In this video we'll start discussing double integrals, and first we'll take them over rectangles. So our aim is to compute the volume under the graph of a function of two variables. So just like in single variable calculus, the definite integral gave us the area under the graph of a function, the double integral will give us the volume under the graph of a function of two variables. So let me just repeat. Our aim is to find the signed volume under the graph of some given function of two variables f of x and y over a rectangle that's the domain of our function this rectangle I'll denote capital R, and it's defined as the Cartesian product of two intervals AB and CD. So these are two closed intervals. So the rectangle itself is a closed rectangle consisting of the points in the xy plane for which x is between a and b and y is between c and d. Okay, so this is our aim, and to help you imagine how we'll approach and solve this problem, let me show you this figure. Here we see the graph of a function of two variables. The function is 2 minus x squared minus y squared, and the rectangle is the square actually from minus 1 to 1 cross minus 1 to 1. So that's just a square of side length 2, centered at the origin, with center having its center in the origin. So and we'll try to find the volume that under the graph of this function. So, and we'll do that as follows. We'll start subdividing this rectangle, this rectangle in the xy plane that we have, into smaller subrectangles, and put boxes under the graph of the function, and the volumes of these boxes will add up to an approximation of the volume under the graph of the function. So as we subdivide into finer and finer subrectangles, we'll get a better and better approximation of the volume under the graph of the function. So this is the basic idea, and now let me actually show you how we do this. So it's as I said, we'll divide R into subrectangles by basically dividing these intervals, chopping them up into smaller subintervals. So what we'll do is we'll take the interval a to b and introduce these cutting points, x0 being a, and then the first point where we cut is x1, then x2, all the way to xm minus 1, and xm being b. So with these cutting points we obtain m subintervals whose union give us the interval AB, and similarly we do the same thing for the interval CD by introducing these y sub 1 all the way to y. Well, we could have a different number of subintervals. Let's call this n, little n, is the number of subintervals that we introduce in the interval CD. with this, well, we can do this in various ways, introducing these cutting points at different places, but we'll do it in a way where these subintervals are all of equal length along in the interval AB and also in the interval CD, meaning that these cutting points xi can be all expressed as follows. It's a plus I times the length of each subinterval, and I'll call this length delta x. And of course, this length delta x, if I want these subintervals to all have the same length, it has to be the total length of our interval, that's b minus a, divided by the number of subintervals that I want to get, which is m. Okay, so this is how I get these cutting points along the x interval, and similarly I can express yj as c plus j times delta y, with delta y being the length of each subinterval, and that should be the total length of our interval divided by the number of subintervals I want to get, and j goes from 0 to 1 all the way to n. So this way I obtained these subrectangles that I mentioned. These subrectangles can be denoted by r sub ij. So these are the Cartesian products of the intervals, the closed intervals xi minus 1 xi and yj minus 1 yj. Okay, and each of these subrectangles has area well, the length of each of these intervals is delta x and delta y, so its area is, well, let's call it delta A, and it's just the product of delta x and delta y, with delta x and delta y being these quantities. Okay, so now that we subdivided our rectangle into smaller subrectangles, now we can again try and approximate the volume by having these boxes in the subdivided rectangle. So each of these boxes has a base with area delta A, and the height of each of these boxes is given by the value of the function at a point chosen from within each subrectangle. Okay, so let me now take these sample points xi star xyj star. Okay, so xi star yj star is chosen from the subrectangle rij, and it's called a sample point. This point could be anywhere, could be chosen anywhere from the subrectangle, and then this quantity, the value of the function at that sample point, will give us a potential height for the box that we want to use to approximate the volume of the graph, the volume under the graph of the function. So this is the height of that box, and the base has area delta A. So this would be the volume of a single box, and when you want to have the total approximation, the total volume of these boxes, so we have to sum over j going from 1 to n, and also over I going from 1 to m. So this double sum is a Riemann sum, but now it's a double Riemann sum. Okay, so this right here is a double Riemann sum, which is an approximation of the volume that we want to find. Now, the volume will the actual volume will be the limit of this quantity as m and n go to infinity, provided that limit will exist. So that's our double integral. So our definition of a double integral, so the double integral of our function f of xy over the rectangle R is the following limit. Well, it's denoted by with this integral sign. Now we have a double integral over R of f x and y dA. So this is the notation for the double integral, that is the limit of such a Riemann sum as m and n go to infinity. Provided that this limit exists. So now that we know how the double integral is defined, next we'll learn how we can actually compute double integrals to find the volume that we are after.